When we look up at the night sky and find the three bright stars forming Orion's belt, we're actually using one of humanity's oldest celestial signposts, a guide that has oriented travelers, inspired myths, and sparked curiosity for thousands of years. But just below that famous belt, in what appears to be Orion's sword, lies something far more extraordinary than any ancient storyteller could have imagined. There, approximately 1,344 light-years from Earth, exists a cosmic factory of unimaginable scale and beauty, a place where stars are being born right now, at this very moment, in a process that has been ongoing for millions of years and will continue for millions more. This is the Orion Nebula, known to astronomers as Messier 42 or NGC 1976, and it represents one of the most studied, photographed, and scientifically significant objects in our entire galaxy. The Orion Nebula isn't just another pretty picture in space. It's a massive stellar nursery, a region where the raw materials of the universe are being transformed into new suns, new planetary systems, and potentially new worlds where life might one day emerge. The nebula spans roughly 24 light-years across, which means that even traveling at the speed of light, it would take you nearly a quarter of a century to cross from one side to the other. To put this in perspective, if we were to scale down the nebula so that Earth was the size of a grain of sand, the Orion Nebula would still be larger than the entire solar system we know today. This is a structure of almost incomprehensible magnitude, and yet it represents just a tiny fraction of our Milky Way galaxy. What makes the Orion Nebula particularly special among the thousands of nebulae scattered throughout our galaxy is its proximity to Earth and its brightness. It's the closest region of massive star formation to our solar system, which means we can study it in detail that would be impossible for more distant stellar nurseries. On a clear, dark night, away from city lights, you can actually see the Orion Nebula with your naked eye as a fuzzy patch of light. This makes it one of the few deep sky objects visible without any optical aid whatsoever. Ancient astronomers noticed this fuzzy star thousands of years ago, but they had no idea what they were looking at. The Mayan civilization observed it, Chinese astronomers recorded it, and it appears in the star catalogues of numerous cultures throughout history, but it wasn't until the invention of the telescope that humanity began to understand the true nature of this cosmic wonder. The first telescopic observation of the Orion Nebula is credited to Nicolas Claude Fabry de Peiresc in 1610, the same year that Galileo Galilei turned his telescope toward the heavens and revolutionized our understanding of the cosmos. But it was Charles Messier, the famous French astronomer and comet hunter, who gave the nebula its most well-known designation when he included it as the 42nd entry in his catalogue of objects that could be confused with comets. Messier wasn't particularly interested in nebulae, he was trying to find comets, and these fuzzy, stationary objects kept getting in his way. Little did he know that his catalogue of cosmic annoyances would become one of the most important astronomical references ever created, and that Messier 42 would become one of the most famous entries in that catalogue. When we look at images of the Orion Nebula today, captured by powerful telescopes like the Hubble Space Telescope or ground-based observatories equipped with adaptive optics, we see a spectacular display of colors, swirling clouds, glowing gas, and bright stars embedded in the cosmic mist. But what exactly are we looking at? What is this nebula made of, and why does it glow with such ethereal beauty? The Orion Nebula is primarily composed of hydrogen gas, the most abundant element in the universe, along with significant amounts of helium and trace quantities of heavier elements like oxygen, nitrogen, and carbon. These elements exist in the form of an enormous cloud of gas and dust, with a total mass estimated to be around 2,000 times the mass of our Sun. This might sound like a lot, but it's important to remember that this mass is spread across a volume of space measuring 24 light-years in diameter. Which means the density of the nebula is actually incredibly low by everyday standards. If you were floating inside the Orion Nebula, you would be in what we would consider a nearly perfect vacuum, with just a few atoms per cubic centimeter, far less dense than the best vacuum we can create in laboratories on Earth. The spectacular colors we see in images of the Orion Nebula aren't just random. They tell us about the chemical composition and physical processes occurring within this cosmic cloud. The predominant red and pink hues come from hydrogen atoms that have been energized by the intense ultraviolet radiation from hot, young stars embedded within the nebula. When this radiation strikes a hydrogen atom, it can knock the electron to a higher energy level or strip it away entirely, ionizing the atom. When the electron falls back down to a lower energy level or recombines with the hydrogen nucleus, it releases energy in the form of light at specific wavelengths, and one of the strongest of these emission lines is in the red part of the spectrum, at 656.3 nanometers, which astronomers call hydrogen alpha or H-alpha radiation. The greenish hues in many nebula images come from doubly ionized oxygen, while blue regions often indicate light scattered by dust particles or emission from ionized helium and other elements. Professional astronomical images often combine data from multiple filters and wavelengths, sometimes including infrared and ultraviolet light that our eyes cannot see, and then map these invisible wavelengths to visible colors so we can appreciate the full complexity of these cosmic structures. At the heart of the Orion Nebula lies a group of stars known as the Trapezium cluster, named for the trapezoidal pattern formed by its 4 brightest members. These stars, designated Theta, 1 Orionis A, B, C, and D, are extremely hot, massive, and young by astronomical standards. The most massive of these, Theta, 1 Orionis C, is a true monster, with a mass about 40 times that of our Sun and a surface temperature exceeding 40,000 Kelvin, compared to our Sun's relatively cool 5,800 Kelvin. This star alone produces more energy in a few seconds than our Sun does in an entire year. It's this incredible energy output, primarily in the form of ultraviolet radiation, that illuminates the surrounding nebula and causes it to glow so brilliantly. The Trapezium stars are incredibly young, having formed only about 1 to 2 million years ago. To put this in cosmic perspective, when these stars were born, our planet Earth was already 4.5 billion years old, modern humans were walking across Africa, and the dinosaurs had been extinct for more than 60 million years. These stars are stellar infants, and they're still in the process of settling into their main sequence lives. But the Trapezium stars are not alone in the Orion Nebula. Modern observations, particularly those made with infrared telescopes that can peer through the thick dust clouds that obscure visible light, have revealed that the nebula contains thousands of stars and protostars in various stages of formation. Some of these objects are still completely embedded in their natal cocoons of gas and dust, invisible to optical telescopes but glowing brightly in infrared wavelengths as they gravitationally contract and heat up. Others have cleared away much of their surrounding material and are beginning to shine as newborn stars, though they may still be surrounded by disks of gas and dust from which planets might eventually form. This is one of the most exciting aspects of studying the Orion Nebula because we're not just seeing stars, we're potentially witnessing the birth of entire planetary systems, cosmic creations that might one day host their own worlds, and perhaps even their own forms of life. The process of star formation in the Orion Nebula follows the same basic principles that govern stellar birth throughout the universe, but seeing it happen in such detail and on such a massive scale provides astronomers with an unparalleled laboratory for understanding how stars and planets come into being. It all begins with gravity. The interstellar medium, the thin gas that exists between the stars in our galaxy, isn't perfectly uniform. There are regions where the density is slightly higher than average, and these regions exert a slightly stronger gravitational pull on the surrounding material. Over time, spanning hundreds of thousands or millions of years, more and more material falls toward these denser regions, and the gravitational force becomes stronger, pulling in even more gas and dust. Eventually, a cloud becomes massive enough and dense enough that its own gravity overwhelms the pressure forces trying to push outward, and the cloud begins to collapse. This is the moment when star formation truly begins. As the cloud collapses, it fragments into smaller clumps, each of which can become an individual star or, in many cases, a multiple star system, since most stars in the galaxy actually exist in binary or higher-order systems rather than being solitary like our Sun. Each collapsing clump grows denser and hotter at its center as gravitational potential energy is converted into thermal energy. The temperature and pressure at the core continue to rise, and the protostar begins to emit radiation, first in the infrared and eventually across the electromagnetic spectrum. This phase can last for hundreds of thousands of years, during which the protostar is still gathering mass from its surrounding envelope and hasn't yet achieved the stable equilibrium that characterizes a true star. The protostar is essentially a gravitationally bound ball of hot gas that's getting progressively hotter and denser, but it's not yet performing the nuclear fusion reactions that will define it as a proper star. Eventually, if the protostar accumulates enough mass, the temperature and pressure at its core reach a critical threshold, typically around 10 million Kelvin for hydrogen fusion. At this point, protons, which are hydrogen nuclei, begin to overcome their mutual electromagnetic repulsion and come close enough together for the strong nuclear force to bind them into helium nuclei through a series of reactions known as the proton-proton chain or, in more massive stars, the CNO cycle. This is nuclear fusion, the same process that powers hydrogen bombs but controlled and sustained by the immense gravitational pressure of the star itself. The energy released by fusion creates an outward pressure that balances the inward pull of gravity, and the star enters what astronomers call the main sequence, a stable phase of stellar evolution that can last for millions, billions, or even trillions of years depending on the star's mass. Our Sun has been in its main sequence phase for about 4.6 billion years and will remain there for another 5 billion years or so, but the massive stars in the trapezium will burn through their fuel in just a few million years because they're so much more massive and burn their fuel at a far more prodigious rate. The star formation process in the Orion Nebula is made even more complex and interesting by the feedback effects that young stars have on their environment. The intense ultraviolet radiation from massive stars like those in the trapezium doesn't just make the nebula glow beautifully, it also heats and ionizes the surrounding gas, creating what astronomers call an HIA region, where most of the hydrogen has been ionized by the energetic photons. This ionized gas is hot, with temperatures reaching 10,000 Kelvin or more, and it has a tendency to expand outward, pushing against the surrounding neutral gas and creating shock waves and compression zones that can actually trigger new rounds of star formation in the areas they compress. At the same time, the radiation pressure from these massive stars and the powerful stellar winds they produce, which are streams of charged particles flowing outward at speeds of thousands of kilometers per second, blow away much of the remaining gas and dust in their vicinity, eventually clearing out large cavities in the molecular cloud. This creates the beautiful sculpted structures we see in nebula images, where glowing gas appears to have been carved into pillars, waves, and intricate shapes by the relentless pressure of starlight and stellar winds. One of the most fascinating discoveries made in the Orion Nebula involves what astronomers call proplyds. which is short for protoplanetary disks. These are disks of gas and dust surrounding young stars, and they're the birthplaces of planets. The Hubble Space Telescope has captured incredibly detailed images of dozens of proplyds in the Orion Nebula, and these images have revolutionized our understanding of planet formation. The proplyds appear as dark silhouettes against the bright background of the glowing nebula, or sometimes as objects with bright edges where the disk material is being illuminated and ionized by the ultraviolet radiation from nearby massive stars. By studying these objects, astronomers can observe planetary systems in the process of forming, seeing the same kinds of processes that must have occurred in our own solar system 4.6 billion years ago when the Sun and its family of planets were coming into being. However, the environment of the Orion Nebula is actually quite hostile to planet formation compared to quieter regions of the galaxy. The intense ultraviolet radiation from the Trapezium stars and other massive stars in the region doesn't just illuminate the proplyds, it also heats them up and can actually evaporate the outer layers of these disks, driving material away before it has a chance to coalesce into planets. This process, called photoevaporation, can be seen directly in Hubble images where some proplyds have long tails of material streaming away from them, like comets made of gas and dust being blown by the stellar wind. Astronomers estimate that a proplyd near the Trapezium stars might lose a significant fraction of its mass in just 100,000 years or so, which is very fast on astronomical timescales. This raises interesting questions about whether planets can form at all in such extreme environments, or whether the planetary systems that do manage to form end up being very different from quieter systems like our own solar system. Some studies suggest that only the inner, denser regions of these disks might survive long enough to form rocky planets, while the outer regions that might form gas giants like Jupiter and Saturn are simply evaporated away. This means that planetary systems born in environments like the Orion Nebula might preferentially produce compact systems of rocky worlds rather than the kind of diverse system we have in our own cosmic neighborhood. The Orion Nebula is part of a much larger structure known as the Orion Molecular Cloud Complex, which is one of the most active star-forming regions in our local area of the galaxy. This complex includes several well-known objects including the Horsehead Nebula, the Flame Nebula, and Barnard's Loop, along with numerous other nebulae, dark clouds, and stellar clusters scattered across the constellation of Orion. The entire complex spans hundreds of light-years and contains enough raw material to form hundreds of thousands of stars. The fact that all of these structures are related, part of one giant molecular cloud complex, tells us that star formation isn't a random, isolated process but rather something that happens in hierarchical structures on multiple scales, from individual protostars to stellar clusters to giant molecular clouds that can spawn entire generations of stars. Within this broader context, the Orion Nebula represents just one particularly active and visible region, but it's connected through the flow of gas, the propagation of shockwaves, and the complex gravitational interactions to all the other star-forming regions in the complex. This interconnectedness means that the formation of stars in one region can influence what happens in neighboring regions, creating a kind of cascade of star formation that can propagate through a molecular cloud over millions of years. Some theories suggest that the massive stars born in one generation can trigger the formation of new stars in nearby gas clouds through their radiation and stellar winds, leading to sequential star formation where each generation of stars influences the birth of the next. This might explain why we see stars of different ages clustered together in some regions, suggesting multiple episodes of star formation occurring in waves rather than all at once. The study of the Orion Nebula has been revolutionized by advances in telescope technology and observational techniques. When astronomers first looked at the nebula with early telescopes, they could see the basic structure and the brightest stars, but most of the detail we appreciate today was completely invisible to them. The development of photography in the 19th century allowed astronomers to make long exposures that could capture far more detail and fainter structures than the human eye could see, revealing the true complexity and extent of the nebula for the first time. But photography using visible light only tells part of the story because much of the action in star-forming regions happens behind thick veils of dust that block visible light completely. The solution came with the development of infrared astronomy, which really took off in the latter half of the 20th century and continues to advance rapidly today. Infrared light has longer wavelengths than visible light, and crucially, it can pass through dust clouds that are completely opaque to visible light. This means that infrared telescopes can see deeply embedded protostars, warm dust, and other phenomena that are completely invisible to optical telescopes. Ground-based infrared observatories, space telescopes like the Spitzer Space Telescope and now the James Webb Space Telescope, have revealed an entirely different view of the Orion Nebula, showing thousands of previously unseen stars and protostars, mapping the temperature and density structure of the dust clouds, and providing insights into the earliest stages of star formation that were previously impossible to study. The James Webb Space Telescope, with its unprecedented sensitivity and resolution in the infrared, has captured images of the Orion Nebula that reveal details down to the scale of individual protoplanetary disks, showing structures that were barely hinted at in earlier observations. These images reveal intricate networks of filaments, jets of material shooting out from young stars, bow shocks where stellar winds collide with the surrounding gas, and countless other phenomena that help astronomers piece together the complex story of how stars are born. Radio astronomy has also made crucial contributions to our understanding of the Orion Nebula. Different molecules in space emit radiation at specific radio wavelengths, and by tuning radio telescopes to these wavelengths, astronomers can map the distribution of various chemical species throughout the nebula. Carbon monoxide, ammonia, water vapor, formaldehyde, methanol, and dozens of other molecules have been detected in the Orion Nebula, each providing clues about the physical conditions and chemical processes occurring in different regions. Some of these molecules are quite complex, containing 6, 7, or even more atoms, and their presence raises intriguing questions about how chemical complexity develops in space and whether the organic molecules necessary for life might be forming in stellar nurseries like Orion. The detection of these molecules also helps astronomers understand the temperature and density structure of the nebula, because different molecules form and survive under different conditions. Cold, dense regions deep within molecular clouds might harbor complex organic molecules that would be destroyed by radiation in the more exposed regions of the nebula. One particularly interesting aspect of the Orion Nebula that has emerged from detailed observations is its three-dimensional structure, which is far more complex than it appears in two-dimensional images. The nebula isn't just a flat cloud, it's a complex, layered structure with different regions at different distances from Earth and at different stages of evolution. The bright central region that we see so clearly is actually a relatively thin layer of ionized gas on the surface of a much larger molecular cloud. Behind this glowing surface lies the dark, cold, dense molecular cloud where most of the active star formation is actually taking place. The massive stars of the Trapezium have essentially blown a bubble in this cloud, creating a cavity of hot, ionized gas surrounded by the cooler, denser material of the molecular cloud. We see the nebula from an angle that looks into this cavity, giving us a clear view of the Trapezium stars and the immediate surrounding regions. But there are vast regions of active star formation behind and around the visible nebula that we can only study using infrared and radio observations. Advanced computer simulations have become an essential tool for understanding the Orion Nebula and star formation in general. These simulations model the complex interplay of gravity, gas pressure, magnetic fields, radiation, and turbulence that governs how molecular clouds collapse and fragment to form stars. The equations governing these processes are incredibly complex and nonlinear, meaning that small changes in initial conditions can lead to very different outcomes, making star formation a chaotic process in the mathematical sense. Modern supercomputers can simulate the collapse of a molecular cloud and the formation of stars within it, tracking individual parcels of gas as they move through the cloud, heat up, cool down, collide with other parcels, and eventually become incorporated into forming stars. These simulations have revealed that turbulence, random chaotic motions within the gas cloud, plays a crucial role in determining where and when stars form. Turbulence creates regions of compression and rarefaction, and it's in the compressed regions that gravity can overcome pressure and initiate collapse. Magnetic fields also play a surprisingly important role in star formation, one that wasn't fully appreciated until relatively recently. Interstellar gas isn't electrically neutral, it contains ions and free electrons, and these charged particles interact with magnetic fields that thread through the galaxy. These magnetic fields can provide support against gravitational collapse, essentially adding an extra pressure that has to be overcome before a cloud can form stars. In some cases, the magnetic pressure can be strong enough to prevent collapse entirely, leaving clouds that might otherwise form stars in a stable, non-collapsing state. The process by which clouds overcome magnetic support and begin collapsing is complex and involves mechanisms like ambipolar diffusion, where neutral atoms gradually drift through the magnetic field over long timescales, eventually allowing the densest regions to decouple from the magnetic field and collapse. Observations of the Orion Nebula using specialized instruments that can measure the polarization of light from dust grains, which align themselves with magnetic field lines, have revealed intricate magnetic field structures throughout the nebula, showing field lines that are tangled, twisted, and compressed by the turbulent motions of the gas. The life cycle of the Orion Nebula itself is something worth considering. This nebula hasn't always existed, and it won't exist forever. The molecular cloud from which the Orion Nebula complex formed likely came into being tens of millions of years ago through the accumulation of gas in the Orion spiral arm of our galaxy. Perhaps triggered by the shockwave from a distant supernova explosion or by the gravitational effects of the galaxy's spiral density wave, this gas began to accumulate and cool, eventually reaching densities where it could resist the dispersing effects of turbulence and begin the process of star formation. The first generation of stars formed in the complex might have been massive stars that lived fast and died young, their supernova explosions enriching the remaining gas with heavy elements and perhaps triggering new waves of star formation. The Orion Nebula as we see it today represents a relatively recent phase of star formation in this complex, with the bright Trapezium stars having formed just 1 million or 2 years ago. But these massive stars won't last forever. In just a few million more years, the most massive of the Trapezium stars will exhaust their nuclear fuel and end their lives in spectacular supernova explosions. These explosions will pump enormous amounts of energy into the surrounding nebula, creating expanding shock waves that will compress, heat, and potentially disperse much of the remaining gas. The explosions might trigger one final wave of star formation in the compressed gas at the edges of the expanding supernova remnant, or they might simply blow away what remains of the molecular cloud, ending star formation in this region. The less massive stars that have already formed will survive these explosions and will gradually drift apart over tens of millions of years, spreading out into the general stellar population of the galaxy and losing their identity as a distinct cluster. Eventually, All that will remain of the Orion Nebula will be a loose association of stars of various ages, an expanding bubble of hot gas from the supernova explosions, and perhaps a few neutron stars or black holes, the collapsed remnants of the most massive stars that once illuminated this cosmic nursery. This cycle of birth, life, and death is constantly playing out in our galaxy and in galaxies across the universe. The material that makes up your body, the iron in your blood, the calcium in your bones, the oxygen you breathe, all of it was forged in the nuclear furnaces of stars that lived and died long before our sun was born. Some of this material came from massive stars that ended their lives in supernova explosions, scattering their enriched contents back into the interstellar medium where it could be incorporated into new generations of stars and planets. Other elements were produced in the final death throes of lower-mass stars that swelled into red giants and gently puffed their outer layers into space as planetary nebulae. The Orion Nebula is participating in this great cosmic cycle right now, taking the raw materials left behind by previous generations of stars and using them to build new stars, new planets, and potentially new worlds where new forms of life might eventually emerge. One of the most profound questions raised by the study of the Orion Nebula concerns the frequency and nature of planet formation. We now know, thanks to missions like the Kepler Space Telescope and ongoing exoplanet surveys, that planets are extraordinarily common in the universe. Most stars appear to have planetary systems, and many of these systems include planets in or near their star's habitable zone, the region where temperatures might allow liquid water to exist on a planet's surface. But the diversity of planetary systems discovered so far is staggering. We've found hot Jupiters, gas giants orbiting closer to their stars than Mercury orbits the Sun. We've found super-Earths, rocky planets larger than Earth but smaller than Neptune, a type of planet that doesn't exist in our solar system. We've found systems where multiple planets orbit in tight, resonant configurations, and systems where planets orbit binary stars or even multiple star systems. The question is, what determines what kind of planetary system forms around a given star? How much of it depends on the mass of the star, how much depends on the composition of the protoplanetary disk, and how much depends on the environment in which the star forms? The Orion Nebula provides a unique laboratory for addressing these questions because we can observe hundreds or thousands of protoplanetary disks all forming under relatively similar conditions in the same molecular cloud. By studying the properties of these disks, their masses, sizes, compositions, and structures, astronomers can begin to understand what factors lead to different outcomes in planet formation. One important discovery is that protoplanetary disks show an enormous diversity even within a single star-forming region. Some disks are massive and extended, containing many times the mass of Jupiter spread over hundreds of astronomical units. Others are compact and low mass, barely enough material to form a few rocky planets. Some disks show clear gaps and rings in their structure, possible signatures of planets that have already formed and are clearing out material along their orbits. Others appear relatively smooth and featureless, perhaps indicating earlier stages of evolution before planet formation has begun in earnest. The composition of protoplanetary disks is also crucial for determining what kinds of planets can form. The solar nebula from which our solar system formed contained about 1 to 2% of its mass in the form of dust and heavier elements, with the rest being hydrogen and helium gas. This might not sound like much, but it was enough to form the rocky planets of the inner solar system and the cores of the gas giants in the outer solar system. In regions of the galaxy where previous generations of stars have enriched the interstellar medium with more heavy elements, protoplanetary disks might have higher metallicities, potentially allowing them to form larger rocky planets or form them more efficiently. Conversely, in regions with lower metallicity, planet formation might be less efficient or might produce different types of planetary systems. The Orion Nebula has a metallicity that's fairly similar to the solar neighborhood, suggesting that planetary systems forming there should, on average, resemble our own solar system, but the extreme radiation environment might favor different outcomes as discussed earlier. Another factor that might influence planet formation is the presence of nearby massive stars. In the Orion Nebula, many of the protoplanetary disks are located within a few light-years of the intense Trapezium stars, and as we've discussed, the ultraviolet radiation from these stars can photoevaporate the outer regions of the disks. But there might be other, more subtle effects as well. The radiation pressure and stellar winds from massive stars can strip away the hydrogen and helium gas from the outer regions of protoplanetary disks, potentially leaving behind disks that are enriched in heavier elements relative to hydrogen. This might affect the types of planets that form, possibly favoring the formation of rocky planets over gas giants, or affecting the atmospheric compositions of planets that do manage to form. Some researchers have even speculated that the intense radiation environment might affect the chemistry of protoplanetary disks in ways that influence the delivery of water and organic molecules to forming planets, potentially affecting the habitability of any worlds that emerge from such hostile nurseries. The study of jets and outflows from young stars in the Orion Nebula has revealed another fascinating aspect of the star formation process. Many young stars, particularly those still actively accreting material from their surrounding disks, produce powerful jets of material that shoot out perpendicular to the disk at speeds of hundreds of kilometers per second. These jets can extend for light years into space, creating beautiful structures called Hubble objects where the jet material collides with the surrounding interstellar medium, creating glowing shockwaves. The Orion Nebula is rich in these phenomena, with dozens of jets and Hubble objects visible in detailed images. The mechanism that produces these jets is thought to involve the interaction between the accreting material, the magnetic field threading through the protoplanetary disk, and the rotation of the system. As material spirals inward through the disk toward the forming star, magnetic field lines can become twisted and wound up by the disk's rotation. These twisted field lines can then channel a fraction of the infalling material out along the rotation axis, accelerating it to high speeds and launching it as a bipolar jet. These jets play an important role in the star formation process by carrying away angular momentum from the system. One of the fundamental problems in star formation is the angular momentum problem. When a large, slowly rotating cloud collapses to form a much smaller star, the rotation rate has to increase dramatically to conserve angular momentum, just like a figure skater spinning faster when they pull their arms in. If all the angular momentum of the original cloud were retained in a final star, the star would be rotating so fast that it would tear itself apart before nuclear fusion could even begin. Something has to carry away most of the angular momentum during the collapse process, and jets and outflows appear to be one of the primary mechanisms for doing this. By launching material outward at high speeds, preferentially along the rotation axis, the system can shed angular momentum and allow the central star to contract to reasonable rotation rates. The protoplanetary disk also plays a role in redistributing angular momentum. With gravitational torques and magnetic effects moving angular momentum outward through the disk while allowing material to move inward toward the star. The colors and structures we see in detailed images of the Orion Nebula also reveal information about the nebula's ionization structure and the way radiation propagates through the cloud. The boundary between the ionized HII region and the neutral molecular cloud is not sharp but rather a complex transition zone where the properties of the gas change gradually. Astronomers call this transition region the photodissociation region or PDR. In a PDR, the intense ultraviolet radiation from nearby stars is still strong enough to break apart molecules and heat the gas, but not quite energetic enough to fully ionize hydrogen atoms. This creates a unique chemical and physical environment where certain molecules and ions exist that wouldn't be found in either the fully ionized HII region or the fully neutral molecular cloud. Studying PDRs helps astronomers understand how radiation from stars affects their surroundings and how energy is transferred from stars to the interstellar medium. The edge of the Orion Nebula, where the ionized gas meets the neutral molecular cloud, shows dramatic features that illustrate these processes beautifully. In Hubble images, you can see towering pillars and cliff-like structures where the neutral cloud material has been sculpted by the radiation and stellar winds from the Trapezium stars. These structures are reminiscent of the famous pillars of creation in the Eagle Nebula, but in the Orion Nebula we can see them from multiple angles and study them in greater detail because the nebula is so much closer. The pillars form because the density of the neutral cloud isn't uniform. Denser clumps of material can resist the erosive effects of radiation and stellar winds better than lower density regions, so as the general cloud surface is pushed back by radiation pressure, these denser clumps are left behind as pillars pointing back toward the ionizing stars. Often, there's a young star or protostar embedded in the dense material at the head of these pillars, and its own gravity helps hold the material together against the dispersive forces. Over time, these pillars will be eroded away, but they may exist long enough for the embedded stars to finish forming and emerge from their cocoons. The Orion Nebula has been a crucial testing ground for theories of massive star formation, which remains one of the more poorly understood aspects of stellar evolution. Massive stars, those with masses more than about 8 times the mass of the Sun, are rare compared to lower mass stars, but they have a disproportionate impact on their environments and on the evolution of galaxies as a whole. They produce most of the ultraviolet radiation that ionizes nebulae. They drive powerful stellar winds that can sweep up and heat enormous volumes of gas, and they end their lives in supernova explosions that are among the most energetic events in the universe. Despite their importance, the process by which massive stars form is still debated among astronomers. The problem is that massive stars are so luminous that their radiation pressure should, in theory, halt the accretion of material onto the forming star well before it reaches the masses we observe for the largest stars. So how do stars with masses of 20, 40, or even more than 100 solar masses manage to form? Several competing theories have been proposed to explain massive star formation. One idea is that massive stars form through essentially the same process as lower mass stars, just scaled up, with continuous accretion through a disk despite radiation pressure. Theoretical work suggests that if the accretion disk is dense enough and if the flow of material is not perfectly symmetric, radiation can escape preferentially in certain directions while material continues to fall in from other directions, allowing accretion to continue to much higher masses. Another theory proposes that massive stars form through the competitive accretion of material in a dense stellar cluster, where multiple forming stars are competing for the same reservoir of gas. And the stars that happen to be near the center of the gravitational potential well can grow to large masses by accreting material that would otherwise have gone to other stars. Yet another idea is that massive stars might form through the mergers of lower-mass protostars in dense stellar environments. The truth might involve elements of all these processes, and the Orion Nebula, with its population of massive stars in various stages of formation, provides crucial observational data to test these theories. Observations of the Trapezium stars themselves reveal that they're not yet fully settled into main sequence equilibrium. They're still contracting, still heating up, and may still be accreting small amounts of material from their surroundings. This places them in a phase of stellar evolution called the pre-main sequence phase, which for massive stars can last anywhere from a few thousand to a few 100,000 years. During this time, the stars are variable, their luminosity and temperature fluctuate as they undergo various instabilities and as their accretion rates vary. Some young massive stars show enormous outbursts where their brightness increases by factors of hundreds or even thousands over relatively short periods, possibly due to sudden increases in accretion rate or instabilities in their envelopes. While the Trapezium stars haven't shown such dramatic outbursts in recorded history, their long-term monitoring reveals subtle variations that provide insights into their internal structure and evolution. The Orion Nebula has also proven valuable for understanding binary and multiple star systems. A large fraction of the stars in the nebula, possibly the majority, exist in binary or higher-order multiple systems. This is actually typical for star-forming regions and for stars in the galaxy generally. Single stars like our Sun are somewhat unusual. Binary star formation can occur when a collapsing cloud fragments into two or more pieces that orbit each other while continuing to accrete material, or when a single rotating disk becomes gravitationally unstable and breaks apart into multiple objects. The Trapezium itself is a multiple star system, with the 4 bright stars visible in small telescopes accompanied by at least 2 fainter companions that orbit some of the brighter members. Detailed observations have revealed that Theta 1 Orionis C, the most massive and luminous of the Trapezium stars, is actually a binary system with a companion star orbiting it every 11 days or so. This companion star is itself quite massive, with an estimated mass around 15 solar masses, but it's completely overwhelmed by the light from its more massive sibling and can only be detected through careful analysis of the system's spectrum and light curve. The presence of so many binary and multiple star systems raises interesting questions about planet formation. Can planets form in binary star systems, and if so, how do their orbits and properties differ from those in single star systems? The answer, from both theoretical modeling and the detection of exoplanets in binary systems, is that yes, planets can form around binary stars, but the configuration of the system depends on the separation of the stars. If the two stars are very close together, planets can form in circumbinary orbits, orbiting around both stars. If the stars are farther apart, planets might form around one star or the other in circumstellar orbits. The gravitational perturbations from the companion star can affect the planet formation process, potentially truncating protoplanetary disks or exciting the eccentricities of planetary orbits, leading to systems that are dynamically more excited than those around single stars. Some of the most interesting exoplanet systems discovered to date orbit in binary systems, including planets like Tatooine from Star Wars with 2 suns visible in their sky. One aspect of the Orion Nebula that often goes unmentioned but is scientifically important is the population of brown dwarfs found within it. Brown dwarfs are substellar objects that formed like stars from the collapse of gas clouds but never accumulated enough mass to sustain hydrogen fusion in their cores. They occupy a mass range between about 13 and 80 Jupiter masses, where 13 Jupiter masses is roughly the minimum mass needed to fuse deuterium, a heavy isotope of hydrogen, and 80 Jupiter masses is roughly the minimum mass needed to sustain regular hydrogen fusion. Brown dwarfs are dim and cool compared to true stars, with surface temperatures ranging from a few hundred to a few thousand Kelvin, making them glow primarily in the infrared. They're difficult to detect and study, but infrared surveys of the Orion Nebula have revealed hundreds of them. The existence of brown dwarfs raises questions about the star formation process and about the minimum mass that can form through the gravitational collapse of a gas cloud. Is there a continuous distribution of masses from the smallest stars down through brown dwarfs to giant planets, or is there a fundamental difference between objects that form from collapsing gas clouds versus objects that form in protoplanetary disks? The boundary between brown dwarfs and planets remains one of the most debated topics in astronomy, not just because of the mass overlap, where the most massive planets might be more massive than the least massive brown dwarfs, but because of the fundamental question of formation mechanism. Does it matter more how an object formed or what its final mass is? A 10 Jupiter mass object that formed from the collapse of a gas cloud might be called a brown dwarf, while a 10 Jupiter mass object that formed in a protoplanetary disk through core accretion would be called a planet, even though they might end up with identical physical properties. The Orion Nebula, with its population of brown dwarfs and its numerous protoplanetary disks, provides a laboratory for studying both formation mechanisms simultaneously and understanding the continuum of objects from stars to planets. As we look at the Orion Nebula today, we're witnessing a snapshot of a process that has been ongoing for millions of years and will continue for millions more. But this snapshot is fleeting on cosmic timescales. The massive stars that illuminate the nebula so beautifully are already racing toward their doom, burning through their nuclear fuel at prodigious rates that will see them explode as supernovae in just a few million years. When those explosions occur, they will mark the end of the Orion Nebula as we know it. The shock waves will disperse the remaining gas, the brilliant glow will fade, and the stellar nursery will close its doors. But this ending is also a beginning, because the material scattered by those supernovae will carry with it the heavy elements forged in the hearts of those massive stars, enriching the interstellar medium and providing the raw materials for future generations of stars and planets. Perhaps, billions of years from now, some of the stars being born in the Orion Nebula right now will host civilizations of their own. Perhaps beings will look up at their night sky and wonder about their place in the cosmos, just as we do. They might discover that their star, their sun, was born in a great stellar nursery alongside thousands of siblings, most of which have long since drifted away across the galaxy. They might find, encoded in the elemental abundances of their world, the signature of ancient supernovae that enriched the cloud from which their system formed. They might even detect, in the motions of nearby stars or in the archaeological record of their own planet, evidence of the violent birth of their stellar neighborhood in a place that we call the Orion Nebula. The story of the Orion Nebula is ultimately the story of how the universe transforms simple hydrogen and helium, the primordial elements created in the Big Bang, into the incredible diversity and complexity we see around us. It's the story of how gravity, working patiently over millions of years, can pull together diffuse gas to create dense stellar furnaces where nuclear reactions forge new elements. It's the story of how those stars then return their enriched contents to space, either gently through stellar winds and planetary nebulae, or violently through supernova explosions, seeding the cosmos with the building blocks of planets. Of life, of consciousness itself. Every atom in your body was once part of a nebula like Orion, drifting through space as a cold, dark cloud of gas and dust. Those atoms were pulled together by gravity, compressed and heated, perhaps cycled through multiple generations of stars, scattered by supernova explosions, gathered again into new clouds, until finally, 4.6 billion years ago, they became part of the solar nebula that formed our Sun, our Earth, and ultimately, you. When you look up at the Orion Nebula on a clear winter night, you're not just seeing a beautiful astronomical object, you're looking at a cosmic cradle, a place where the future is being written in fire and gas and gravity. You're seeing the process that created our own solar system playing out before your eyes, delayed by 1,344 years because of the time it takes light to cross the vast distance between us and that stellar nursery. The light entering your eyes left the Orion Nebula in the late 7th century, when the world was a very different place, when the great libraries of the ancient world still held knowledge now lost to time, when humans had no conception of the true nature of the stars or the vast scales of space and time that govern the cosmos. The Orion Nebula reminds us that we are part of something much larger than ourselves, a cosmic cycle of birth and death and rebirth that has been playing out for billions of years and will continue for billions more. It tells us that we are made of star stuff, as Carl Sagan so eloquently put it, that the very atoms that make up our bodies were forged in stellar furnaces and scattered across the galaxy by dying stars. It shows us that planet formation and possibly the emergence of life is not a rare accident but a natural consequence of the laws of physics playing out across the universe. And it inspires us to keep looking up, to keep exploring, to keep asking questions about our place in this vast and beautiful cosmos, because every answer we find leads to new questions, deeper mysteries, and a more profound appreciation for the universe we inhabit and the incredible journey that brought us here, to this moment, contemplating the birthplace of stars 1,000 light-years away in the Sword of Orion.